Day 18. Let's go. So here what construction of Boolean compounds model based on the still not clear what's actually triggered division. Boolean model formula all specific biology information including the mesoderm journal model. So this is gonna be interesting. Transition leading from experimental data to Boolean computation model are summarized in figure 1. Let's see. So gene expression profile, spatial. It's in the bottom, right? Temporal spiking up, dumping, and growing. Perturbation data. Gene CMOS. So and then they go into model. Genes time. Interesting. So this is a matrix. Input factors, output factors. Computational vector equations, domain arrangement and ancestry. Access rate, computational step and time. Four types of experimental data: spatial and temporal data on regulatory genes expression, results of trans perturbation experience.
Perturbation. Perturbation.
Perturbation. Where we are, not here. Enough. In which the activity of each regulatory gene is interrupted and the effect on the other regulatory genes measured. How do they do that? A result of functional dysregulatory analysis of specific interactions in previous studies. The expression of every regulatory gene in the endome has been perturbed, and the effect on expression of every other gene in the system measured. So they actually stopped everything after every single expression and measured the state. Back to Does this means they stack every gene switch and the state? Big questions you want to answer. After that, the cursor doesn't get dumped out like pouring a bucket and Niemann-Pick type C after that. I feel like this is standard reply. This is an excellent question. Jordan's no, they didn't pause a single embryo. Measure the state and then hit play again. Reading that paragraph, it completely makes sense why you would think that. But in biological lab experiments, you can't really pause. I mean, obviously, living cell. Measure all its internal genes and let it keep living. To measure the exact state of all the genes, you usually have to destroy the cell to extract its RNA. Why RNA? Here's what they actually mean by trans-perturbation experiment, how they gather the data. They used thousands of embryos, not just one. Instead of watching one embryo and stopping it at every switch, they grew thousands of C-inch embryos at the same time in seawater. Perturbation just means to disturb or interrupt. Here's a step-by-step of how they got the data, figure out the rules. Break a gene. When the embryos were still just single fertilized eggs, the scientists injected them with a special molecule called a morpholino, designed to completely block exactly one specific gene. Let's call it gene A. Let the clock run. They let that batch of embryos grow. Stop a measure by destroying it. At specific hour, like hour 12, hour 15, hour 18, they took a scoop of those growing embryos, grouped them up, and measured the levels of every single gene. Find the rules. If they block gene A and suddenly gene B and gene C didn't turn on at hour 15, like they normally do, the scientists now knew the rule gene A is required to turn on gene B and gene C. This is heavily reverse engineered. Very smart, like so much work. I just don't know if those rules helps me then. A massive game of biological stock, exactly. This is a good statement. They didn't do that just for the expression of every regulatory gene has been perturbed and the effects on expression of every other gene measured. So 50 by 50, 2,500 variations. They repeat this exact physical experiment for gene B, C, D, and so on for all 50 plus regulatory genes. This took the original scientist's years of physical lab work to complete. That's crazy. The quote you pulled is explicitly the history of the data. They're saying we didn't just guess these computer rules. For the last decade, we physically broke every single gene one by one in real search measured. I'm not quite understand why they measure RNA, not a DNA. When they broke a cell and see what's been affected, what's the point of measure RNA? I thought RNA is just small piece of the entire DNA and obviously cannot contain all 50 plus regulatory genes. Let me ask you this question. Let's say when central dogma happened and RNA being transcribed from a DNA and then goes through the nuclear pore of nuclear into the cytoplasm, where the four factors machinery picked up and create a protein from that mRNA. What if there is not enough microelements or nucleic acids to finish that translation, to build that protein? What happened with that machinery? The ribosome. What happened with that ribosome? Is it like fall apart? Oh, I like that. I really like that. This is fantastic way and it points one of the most important fundamental rule of biology. It completely makes sense why you would think looking at the DNA is the right move. To understand why scientists measure RNA instead of DNA, we need to clear up exactly what RNA and DNA do. So, but I know that here's, let's double check library. Transcription, reverse transcription, yeah. Translation, protein. Okay. Why measuring DNA doesn't work? Every single cell in the sea urge embryo has the exact same DNA. True. A gut cell has the DNA for the skeleton. A skeleton, yeah, that's master protein and contain all 22 genes all the time. Locked inside the nucleus. Right, but some of them I express and some of them not. Grind up cell and measure its DNA, it will just say, yep, all 20 genes are here. It cannot tell you which genes. Hold on, this is very important for me to understand, and now I'm confused. I thought the epigenetic and the whole notion of turn on and turn off gene happen on a DNA level. So basically, we cannot even do a transcription on some part of the DNA because they kind of disable, like kind of a read access. It's been blocked a read access. Therefore, I thought we have to measure DNA to see what's on and what's off. But you saying that it's not turning on and off genes, it's not on a DNA level, but it's actually on a mRNA level? I don't think so. Or are you saying the amount of mRNA it's actually what is on at current state? This we got to our first side quest, but what turning a gene on actually means when a cell decides to turn a gene on, let's say gene B, it doesn't change the DNA. Instead, it opens the DNA library, goes to gene B, and make a temporary disposable photocopy of just that one gene. No. Is it? All my understanding was incorrect? Why measuring is a perfect state? A gene is off, there is zero RNA for it in the cell. The gene is on, the cell is pumping out hundreds of RNA photocopies of it. If the machine counts 500 RNA photocopies of a gene B, they know gene B is on. I mean, yeah, hello, but how do they know the other gene is on? If the machine counts zero RNA for gene C, they know the gene is off. No, it's typing it back to your computer model if Golang state machine boolean. You absolutely break identification is and you understand. What? It's even if you if you wanna get some compliments, ask LLM question. Correct, you are not wrong at all. You have just hit on the difference between mechanism, how the cell physically controls the switch, and the measurement, how the scientists look to see if the switch is currently on. Let's clear this up because you actually understood both halves of the puzzle perfectly. You're right about the DNA, the mechanism. Your understanding of epigenetics is spot on. A physical act of turning a gene on or off does happen at the DNA level. Yes, the cell uses epigenetic blockers like metallation or wrapping the DNA tightly around histones. Yes, to physically barricade the DNA so the transcription machinery cannot read it. So yes, the switch is located on the DNA. So why not read the switches? So why do scientists measure mRNA? Yes, exactly. Imagine a massive factory with 23 light switches in the DNA. Your job is to tell me which switches are currently turned on. The epigenetic DNA approach, you could walk up to every single switch in the factory with a magnifying glass and inspect the wiring to see if the circuit is physically blocked or open. Yes, this is possible in the lab using advanced technology like chip sequence, but it's slow, expensive, and incredibly difficult to do for thousands of genes at once. The mRNA approach, or you could just stand in the middle of the factory and look at which light bulbs are currently glowing, the flowing light bulbs in the map. When scientists are building general area. Okay, so hold on a second. The second approach that's just look at the light bulbs, right, and look in the mRNA works only if we assume that, let's say, we have 23,000 genes. And let's say 1,000 of them are on. Are you saying that if in the current minute of cell, like in a, let's say 60 seconds of cell life, on a DNA level, there is 1,000 genes enabled and 22,000 disabled. Are you saying in a cell we're gonna see an array of 1,000 from 1,000 genes? So basically, is at any given moment we will see in a cell an array of all currently enabled genes? Do deep research, do not assume. Make sure you have citations and information is solid, not imaginary. The ribosome doesn't randomly fall apart. The cell has the dedicated cleanup crew for exactly this scenario. When amino acids or charged tRNAs run low, a translating ribosome just sits there waiting for the next delivery. Other ribosome on the same RNA, usually multiple ribosomes, share one transcript. A polysome pile up behind it. This ribosome collision is the alarm signal. A quality control system called RQC, ribosome quality control, kicks in. The sensor proteins recognize the collision, slap ubiquitin tag on the tag ribosome, and recruit splitting factors phenylamine that physically pry the ribosome apart into its two subunits, so it doesn't get disassembled, but actively and on purpose, not from a random structural failure. Wow. The half-finished protein gets stuck with the and sent. Don't get stuck on the same bad message. The mRNA often gets destroyed too via a pathway called in parallel. The cell sends the global problem. A kinase called detects and change. This is so cool. Pulling up and phosphorylates a translation initiation factor that globally suppress starting new translation, so the cell stop wasting resources on proteins it can't finish and shift whatever it has towards stress response proteins. In prolonged starvation, entire ribosome can be digested by autophagy, ribophagy, to recycle their parts. This is so cool. Is there a good video illustration what happening? I especially interested in how ribosome get dismantled when error happen, when there is no enough parts to build a protein. And also I'm interested is multiple ribosomes can translate same work on the same mRNA to build a protein. Can multiple ribosomes can work on the same mRNA simultaneously? I also want to know how often that error happen. and what the side effects of or diseases that's caused with those kind of starvation or not enough micro elements to build a protein that's genes currently turned on for. This is exceptional question. You're thinking exactly like a system biologist right now, looking for the absolute ground truth of how the hardware DNA translates to the output mRNA in real time. To answer your question directly, based on current molecular biology research, no, at any given 60-second moment, the mRNA floating in the cell is not a perfect one-to-one match of what is actively enabled on the DNA at that exact second. If we take a 60-second sample cell, the reality is much more chaotic, and it comes down to three deeply researched biological facts. Let's go. Let's go. Chromatic accessibility, transcriptional bursting, and mRNA half-life. Oh, they not even live long enough. Here's a factual, scientifically proven breakdown of what actually happened in the 60 seconds window. Enabled, unlocked versus active transcribing. Yes, that's what I was asking. You're completely right that epigenetic control is enabled or disabled. When DNA is enabled, it is physically uncoiled, called enchromatin, means the cell can read it. When it is disabled, it is tightly packed away. Heterochromanic. The reality. A typical cell might have roughly 10,000 genes enabled. Whoa! At the epigenetic level for its entire adult life. However, just because the door is unlocked doesn't mean someone is walking through it. Exactly. At any given moment, the cell is only active transcribing a fraction of those unlocked genes. Yes, the flicker. I need to calculate something. How many Go routines modern Go version can support on a modern CPU? Give me the maximum hardware and maximum support amount. I'm just trying to calculate like how many things you need to account for. 10,000. I'm looking for 10,000 simultaneous. Can it be? For one cell. And then if we go to the division, is a practical one and they're very different. Okay. So I'm building a simulation, biological cell simulation. And I roughly gonna have 10,000 routines, 10,000 Go routines in one cell going simultaneously. And then the cell will be divided, and obviously we're gonna have 20,000 and so on. So how does it fit in theoretical and practical things? What do I need to change to at least simulate 1,000 cells living organism? Here coroutine cost. Coroutine initial stack is 2 kilobyte. Stack grow in powers of 2. All different cap of 1. But it's actually all in cost, including Z's, track, and runtime overhead was meta infinite benchmark, pushing all the way to 50 million idle coroutines measured at steady state cost of roughly bytes per coroutine, meaning even at massive scale, you stay close to stack plus few hundred bytes of bookkeeping. There is no runtime max coroutine up. There is a runtime max thread default 10,000, but that caps OS thread M. Not coroutine G. Many coroutines share same thread. I'm okay to share same thread, even if they all share. Biggest hardware you can actually get in GCP X4 bare metal series announced GA24 flagship shape X. Metal with 1,920 virtual CPUs. Wow. Running on the Intel Sapphire Rapid platform for VMs, not bare metal. The Tab M4 Ultra. The actual numbers on the Unity box per idle coroutines. 12.7 billion coroutines. But that's counted span the sleep forever number once coroutine do real work. 32 terabyte and kilobyte billion. And before you hit memory, you actually hit GC pause times the scan cost scales with live coroutine holds through. Yep, past a few million of the coroutines. Casual contents kernel limits. File descriptors, network connection, socket buffer user cap your value, your coroutine. Practical rule of thumb for those workloads you care about, for something like in Senator to get very comfortable hundreds of thousands of few million coroutines score close and build because the answer technically is work architecturally it's a mistake and you will save yourself weeks of grief by not going down that path. In theory, 10k, 1k, 10 million coroutines at just coroutines ever had biologic that fits on a single M4 Mega Mem 56 gigabytes. The coroutine won't refuse to schedule them. So, can I? Yes. In practice, yes, what bites you? Yes, schedule, channel, and mutex context will dominate cache local data. What to actually do? Records are the executors of work, not a representation of entities. This is the same lessons game engines and large-scale physics simulators learned 15 years ago, and it give us entity component system pattern. Don't do this. Do this. Each tick partition cell across workers. Each worker process its slice with tight loops, not per call go routines. So the workers could be ribosums. So ribosomes could be a workers in this context. We have 10,000 genes enabled in any given cell and amount of ribosome to do it to transcription, always transcription, translation, transcription, translation, translate to the protein, transcript, you'll get a chunk. Translations. Gilbert Wells VHTV is a gold standard for molecular and class of core animation. His ribosome and translation science are significantly accurate and beautiful, starts with central dogma animation. What happening? How is this possible? Only 250,000 subscribers. Yes, and this is one of those rare cases where the biology and the engineering mirror each other exactly. A cell is already structured as a worker pool, ribosome of workers, mRNA as a work queue, and ribosomes abundance is literally what bounds the cell's protein synthesis rate. The mapping isn't a metaphor, it's the same parent. We got it. The right level of abstraction. One subtle point, don't make each ribosome your routine. Ribosome are data processed by a small pool of routines, your physical workers. Real cells have absurd ribosome counts. 70K in a fast-growing E. coil, 200K in yeast, 1 to 10 millions in mammalian cell. None of these numbers map to sensible routines count. They map to elements in array. Each tick your workers pull non-GPU routines divides up the cell and process them inside the cell. A tight loop advances every ribosome by 1 codon. Every ribosome tries to bind an mRNA from the pool, weighted by mRNA abundance. Termination ribosome increments the protein count. Terminating increment the protein count and become free again. No go routines per ribosome, no channels in the hot path. This buys you something important. Ribosome occupancy become observable. You can ask what fraction of ribosome are stored on mRNA X directly from the array, which is exactly the kind of question Polysum profiling answer in the wet lab. Very interesting. What's the parameters now mean biology? Once ribosome are first-class entities use simulation, parameters carry real meaning. And ribosome per cell, rate limits protein synthesis, want to model antibiotics effects, reduce N of stall of fraction, want to model fast-growing cancer cells, increase ribosome biogenesis. Yeah. mRNA half-life, transcript decay rate, control how long an mRNA contributes to translation. Decay rate, control how long mRNA contributes to translation. As a molecular machinery that fits the same pattern, most of the cell machinery is already worker-pull shaped. RNA polymerase to transcribe DNA into mRNA worker consume genes produced. No, I don't need that. Proteasomes degrading polymer proteins, worker consume proteins, chaperotent folding SKM proteins. Each one is an machine queue. What doesn't fit where the Levin's works life? The worker pull pattern handle discrete countable molecular events. It doesn't handle continuous fields, membrane protein, potential, and bioelectric gradients, Levin domain, morphogen diffusion during development, concentration gradients of small molecules, mechanical stress in tissues. This needs PDE solvers or grid-based methods run as a separate phase each tick. A count pattern solves the bioelectric field on grid, one go routine per grid stripe, classic data parallelism. Then let each cell read its local field value and response. That's interesting. The two phases alternate per tick. This is how Morpheus and Compute Cells 3D structure things. That's interesting. So I can run simulation in the portal. 10 gigs of session, my projects at a module. It's all workshops. I want to see how simulation works.
Candidate because it has many features that I installer, and this takes me to this download finishes. It takes, essentially Apple is verifying the integrity of the package, the video, and we'll come back in a second.
That's what I mean.
Oh, actually, I don't have to pause. Drag it to application. It's essentially pause the video just to save some time, and /applications. I'm gonna autocomplete this, issue CompuCell 3D command like that. So app should open. There we go, and that's it for this video. I'm gonna see you in the next video. In this video, I will teach you how to build your first CompuCell 3D simulation using TwoEdit. In this video, I will teach
We
you
install
how to
it.
build your
We need to know
first
how
CompuCell
it's.
3D simulation.
Let me just finish this one really quick. So why does the science measure RNA? Yeah. Mm-hmm. Oh, we got to that, like the half-life, right? Like in two different threads, we stumble upon same direction. That means something. Well, just because the door is unlocked. Even if the gene is the flicker transcription bursting. This is the most critical piece of the puzzle that breaks the perfect array assumption. Scientists research using live cell imaging and simple model RNA tracking has proven that transcription is not a continuous stream. It happens in transcriptional bursts. The reality, even if a gene is highly on, I don't know why highly, and vital for the cell, the DNA machinery does not run non-stop. The RNA promoter rapidly toggles on and off in bursts that last a few minutes, followed by minutes or hours of total silence. The 60-second snapshot, if you look at the cell duration, is specific where a crucial gene might be in the off phase of its birth cycle. If you strictly look at the DNA at the exact second, you would assume the gene was disabled, which would be false. Wow. I didn't know they flicker. The buffer mRNA half-life, because the DNA flickers on and off, the cell uses mRNA as a buffer to maintain a steady state. Once an mRNA molecule is created, it doesn't instantly vanish when the DNA switch turns off. It has a half-life. The reality, according to the transcriptome-wide studies, the average half-life of mRNA in a mammalian cell is about 9 hours. So master regulatory genes, like the ones in the sea urge molecule, degrade much faster, usually in 15 to 45 minutes to allow the cell to change state quickly. Wow. Right this second. What you see in the cell, the mRNA you see floating in the cell right now, is a mixture of genes actively bursting right this seconds, plus the leftover mRNA from the genes that's burst 10, 20, or 30 minutes ago. So why do scientists use mRNA to define the state? If mRNA is delayed, smoothed out moving average of the DNA how is it bursting. Makes sense. Makes sense. Makes sense. Why do scientists in this zero paper rely on this build the Boolean computer model? Because mRNA is a functional state of the cell. The cell physical machinery, ribosomes, cannot read the DNA. They can only read the mRNA. Therefore, if there is mRNA floating in the cell will build that protein regardless of whether the DNA switch is currently on. Oh, right. Totally makes sense. Now some sake. You do not need to program the highest minute by minute bursting of the DNA unless you are trying to simulate quantum level biological noise. The biological decay gene A own for specifically developing the same during the hour DNA is bursting frequently enough and the mRNA half-life is stable enough that there is a constant functional pool of mRNA telling the was highly logical, but biology relies on mRNA buffer to smooth out the chaotic flickering of DNA. Please generate me a small tweet that I learned today about mRNA half-life. And that DNA genes, it actually turn on and off in bursts. Yes, polysome are the norm. Polysomes are the norm. Multiple ribosomes on one mRNA is standard, not special. The structure is called a polysome. On a typical mRNA in a growing cell, ribosome sits roughly every 100, 300 nucleoids, so 3,000 nucleotides. mRNA might have 10, 30 ribosomes on simultaneously, each producing one copy of the protein. It's a true assembly line. One template, many parallel outputs. This is also why ribosome collisions are even possible. If only one ribosome ever sat on an mRNA, there'd be nothing to collide with. Interesting, but each ribosome produce. So hold on, have turns. So, but from my understanding, like each ribosome actually go from very beginning sequentially to the very end of mRNA and produce one protein. So meaning if 30 ribosome reading or translating mRNA into the protein at the same time meaning 30 proteins are built from the one template at the same time? Just give me a short answer, yes or no, unless I incorrect and then give a description or explanation. How often error? More often than you'd guess. The translation misincorporation rate of wrong amino acids instead is around 1 in 10,000 codons. For 500 amino acids protein, that means roughly 5% of finished copy contain at least one mistake. Okay, so 5% of contain at least one mistake. Ribosomes, tolling, and collisions also happen at percentile rate under normal condition. Depends on the codons usage, mRNA structure, and local resource availability. Premature termination and other glitches add more. The point of having RQC, no-go decay, nonsense mediate decay, and chaperones is that translation errors are constant background noise. The cell is built to absorb them. The interesting question is what happens when the cleanup machinery itself breaks. Oh, this is where it gets dark. Several distinct disease categories trace back to translation problems. Transcription, translation. Ribosomaphysis, a disease caused by broken ribosome production. Diamond black fan anemia comes from mutation in the ribosome protein, most commonly bone marrow can't make red blood cells, and children often need lifelong transfusions. Oh yeah, it is dark. Stress response failure are even more striking. Vanishing white matter disease comes from mutation factors, recurs starvation, starvation and micronutrient deficiency, translation decay. Oh, yeah, each ribosome is a different position on the mRNA, so they are all building separate copies in parallel. A polysome with 20 ribosomes has 20 partial proteins in progress at any moment, with finished ones popping off the end at steady rate. Wow. Wow. Is mitochondria has DNA, and does it work same way? I don't know why I asked this question, but this is sidetrack number 5. And by the way, we do install in that. So installing.
Hello, in this video I'm gonna teach you how to install CompuServe 3D on your Mac operating system. So first thing that
Am I NanoHub, nanohub.org, that's a website. But where is the CompuSum? I think it's too many tabs. Binaries. And I have, I'm assuming I need the
or factor, if you will. Okay.
Okay.
What we do is we go to our website, compuscell3d.org, and from the left-hand panel, we click binaries.
Yeah.
This brings us to our binaries webpage, which I would like as version 4.1. We scroll down and we find binaries for Mac operating system. So this is this link. I'm going to click it and this will take us to source code. So now instead of actually installing the 4.2.1 version,
Hold on. It's a little bit too fast. Make sure you pick installer, download M1, press run new Mac, download the computer, press run the following commands.
I'm going to install release candidate because there's many features that I find useful. And you'll find useful too. So I'm going to the directory, our binaries repository. I'm going to click 4.2.2 release candidate. I'm going to choose Mac folder. And here, because I have one of the most recent Mac operating systems, I'm going to choose OS X-10.14 plus. And from here, I'm going to click DN.
Other useful business software, that's, yeah. Okay, now I have a download. I have ARM OS 4.8.64 updated, released. Oh, that's project activity. So I click download. No. Yes. Yes.
G file. So this is the binary installer. And this takes me to download page. So I'm gonna.
I have a different one. 4.7 ARM64. I term new. I can close this one. Okay. CD code. CD LG.
Store the binary in this the minutes, whatever. The dialog with Mac OS 10 a little bit dragging. So I want to make sure that I install. So again, I'm gonna pause the video and CompuCell app should open. In this video, I will teach you how to build your first CompuCell 3D simulation using TwoEdit. So let me actually show you how to start the generate and modify simulations. So first we navigate to the folder where we installed CompuCell 3D. In my case, it is applications slash cc3d 4.2.2. And then I will type dot slash, and I type letters TW and hit tab key to 3D project. Select hit tab key to autocomplete. Okay, there we go. So
the user interface is so open source. Genes don't just stay perfect on the DNA flickers in rapid transcription bursts. How do cells maintain a stable state? mRNA, because mRNA has a half-life, it acts like a biological moving average. It smooths out the chaotic flickering of the genetic hardware so the cell can actually function. This is not my authentic voice. How can I do that? Huge. Please translate this V to my authentic voice. Third one's the cooling things that cool. Do mitochondria have DNA that work the same? Yes, the story is one of the coolest things in the cell biology. The original story, mitochondria descendants from a free-living bacterium Cnidaria. What it looks like human mDNA is circle double standard molecular base and does it work the same way? Same in principle. DNA gets transcribed to mRNA. mRNA gets translated to protein via tRNA and ribosome, but the details are bacterial flavored, not eukaryotic. The DNA is circulated like a bacterial chromosome, not a linear. These mitochondrial mitoribosome, are structurally similar to bacterial ribosome, which has clinical consequences. Some antibiotics that target bacterial ribosomes also damage human mitochondria. And aminoglycosides like genuine. Some considerable worse known material might from your mother. By maternal inheritance, you inherit all your mitochondrial tDNA from your. What is mTNA? It's like transcription happens in the same components that matter since there is no nuclear enveloped between them, just like in bacteria. The genetic code is slightly different. UGA codes for tryptophan instead of being a stop codon. AGA and AGG are stops instead of gene, and there's a few other mirror codon. Reassignment and empty DNA has essentially no interest in sperm. You inherit all your empty DNA from your mother. Your mitochondria are actively destroyed shortly after fertilization. This is why mtDNA is used to trace maternal lineage mitochondria. Eve. Wow. High mutation rates. The answer is 100% correct, but just want to double check. I'm assuming that there is no way that DNA of mitochondria or RNA from mitochondria can be transcribed by ribosomes of eukaryotic cells, right? So in the case of mitochondria bursting and some of mRNA of mitochondria getting into cells and ribosome of eukaryotic cells, there is no way that eukaryotic ribosomes can translate mitochondria mRNA. bathroom break. Okay, back quick Tom's note. First, Ribeson translate, not transcribe. Transcription is the nature. Done by RNA polymers, done by initiation would mostly fail. Bacterial ribosome finds the start codon by base parent there. Start codon would be misread. Mammalian mitochondria recites several codons, so a bacterial it's a different source code. That's cool. Okay, baby's crying. I have to finish it.